Welcome to Scipy, and welcome to my presentation Leading Magnetic Fusion Energy Science into the Big and Fast Data Lane. Today I present how we are using Python to accelerate research on magnetic fusion energy. You will hear a primer about fusion energy, you will see an example of the data analysis performed for fusion research, and how we use Python to accelerate the data analysis workflow by developing a streaming framework that uses high-performance computing resources. Let's start by looking at the physical principle underlying fusion energy. When the hydrogen isotopes deuterium and tritium fuse as to produce a heavier helium nucleus and a neutron, a part of the atomic binding energy is converted into kinetic energy. This in turn can be used to generate electric energy. Besides this, there are other properties that make fusion energy a desirable energy source. Fusion reactions run the opposite way of fission reactions that power nuclear power plants. So there is no chance of an uncontrolled chain reaction leading to a meltdown. Fuel for nuclear fusion can readily be obtained from seawater. And finally, a back-of-the-envelope calculation shows that 2 kg of fusion fuel is sufficient to power 700,000 homes for a single day. Of course, there is a catch. One needs to confine fusion fuel as a 100 million degree hot plasma to sustain a sufficient rate of fusion reactions. So fusion is difficult. Having to confine a lot of electrically charged particles in a small space only adds to this. Fusion research has been going on for 60 years now. Today, much research in the field is performed in international collaborations. And here we see one of the machines that generates such a magnetic bottle that can confine a fusion plasma. The picture on the left shows a sketch of the ITER tokamak, which is currently under construction in France. ITER is a collaboration between China, the EU, India, Japan, Korea, Russia and the US, and it will be the largest tokamak ever constructed. If you look closely, you can actually see a person standing in front of the machine. ITER is an example of a tokamak, the leading fusion device concept. It creates a magnetic bottle using magnet coils, shown in orange, and a vacuum vessel, shown in white, to confine the fusion plasma in a donut-like shape. In this talk we don't talk about either though, but about one of its predecessor tokamaks called K-Star. This is an operational tokamak in the Republic of Korea. Plasma discharges, we call them shots, in such devices usually last only a couple of seconds, up to a couple of minutes. During the shots, numerous scientific and engineering diagnostics produce vast amounts of data. After each shot, the machine enters an approximately 30-minute long cooldown phase to bring the cryogenic components back to operational temperature. Then the device is ready for the next shot. Now, given that research on fusion energy is performed in international collaborations, we asked how a modern workflow would look like that incorporates the central roles: scientists and engineers around the world, big devices, and big computers. And this is the answer that we came up with. A modern workflow would connect all these distributed resources. Thereby, such a workflow can accelerate scientific discovery by providing actionable analysis results in between shots. Here on this slide you see how such a workflow could look like. It's kind of busy, so let me illustrate the workflow. The workflow starts by running an experiment at a tokamak in Europe. A diagnostic, which is a fast camera in the example shown here, measures a sequence of images. The images are sent to a high-performance compute resource in California. There, an expensive image analysis is performed, for example a machine learning-based anomaly detector. The analysis results are presented in near real time to a scientist who could be located in the east coast of the US. Interpreting these analysis results, the scientists can now communicate with engineers to optimize the experimental setup for the next shot. Okay, this is an example of the workflow we want to enable. Let's get started and take a look at the software we developed for this purpose. In this talk, I was focused on a workflow that uses data from an electron cyclotron emission imaging system, which I introduce you to in the following section. Continuing, we will take a look at the Delta framework, which we are developing to facilitate federated data analysis workflows. After that, I will present the implementation details and some benchmark results of Delta. Following with the conclusions, I will close my talk by addressing some items we are currently working on. Electron cyclotron emission diagnostic systems measure electron temperature fluctuations. As physicists, this information aids us in understanding what is going on in the plasma. The ECE imaging system installed in the K-Star tokamak produces TE measurements, arranged in a set of two two-dimensional arrays 24 by 8 pixels, shown in the left. You see the confined fusion plasma in gray. The two orange rectangles denote the area where the ECE measures TE fluctuations. Here you also see two typical measurements, which show a propagating mode structure. Now the ECE diagnostics sample at a rate of 1 MHz, and it generates data at a rate of about 5 GB per second. For research purposes, scientists often calculate spectral quantities, such as the cross power S, the coherence C, the cross phase P, and the cross correlation R. Input to these are Fourier transform time series, typically about 1 millisecond long. When calculating the FFT of short time chunks of a time series, we sometimes refer to it as the short-time Fourier transformation. From the 192 channels of the ECEI, one can form 18,336 unique channel pair combinations, which serve as input to the spectral quantities. To process all data sampled during an entire shot, this amounts to a very large number of function evaluations. The workflow framework that we are developing is used to calculate all of them using an HPC resource. Now we have defined the data analysis workflow that we want to implement. Let's continue by looking at the architecture of the Delta framework, which is designed to facilitate such a workflow on distributed systems. Delta consists of components that facilitate data loading, forwarding, and processing. These tasks are not necessarily performed on the same resource, so Delta bridges them by using an I/O library with streaming support. The figure shows where the different components of Delta are executed. At the experimental site, K-Star in our example, a generator stages experimental data and streams it to the compute site from a DTN, a data transfer node. At the compute site, the National Energy Research Scientific Compute Center NERSC, in our example, a middleman receives the stream. The middleman uses optimized wide area network streaming methods to receive the data stream and forwards it to the actual compute resource. While the middleman is optional, one may need it in cases where network security policies forbid direct access to HPC resources from the internet. Delta uses the ADIOS library for all I/O tasks. ADIOS is a high-performance parallel I/O library designed for HPC environments. It is commonly used by Department of Energy research codes and freely available on GitHub. It supports streaming using multiple backends such as RDMA and ZeroMQ. It also implements parallel file-based I/O using a custom binary pack format, which is similar to parallel HDF5. At the HPC resource, a processor receives the data stream and orchestrates the distributed execution of the analysis routines. Our example workflow uses Cori, which ranks 13th on the top 500 list. Cori is comprised of 2,388 Xeon Haswell CPUs and 9,688 Xeon Phi Knights Landing coprocessors. Each node is equipped with at least 128 GB of RAM. The software architecture of the generator and the processor is rather simple. The generator uses a loader class to stage experimental data for transport. This data is read batch-wise and passed to a writer, which streams the data to the compute site. In ADIOS, each stream needs to be given a unique name. The processor reads time chunks of experimental data from the stream using a reader object. This data is then passed to a task list object, which is configured to execute the desired data analysis. Each individual spectral quantity is calculated by a task object, which launches an appropriate compute kernel and immediately stores the result of the calculation. For the computational kernels, we try to follow calling conventions from packages like Scipy. Building Delta in such a modular fashion allows us to flexibly change I/O patterns by configuring the writer and reader in the desired way. Modeling the workflow as a series of configurable objects allows us to flexibly set up the desired workflow configuration. As you have just seen, the architecture of the framework is rather simple, but the task we are doing is quite demanding. Especially the processor needs to show solid concurrent I/O and compute performance. Let's continue discussing implementation details. Let's start with inspecting the generator, which usually runs on the DTN. It has a rather simple logic. First, a data loader and a writer are instantiated. The following for loop iterates over time chunks of ECE data, consisting of 10,000 consecutive samples for all 192 channels. These chunks are streamed using the writer. The function calls begin step, put, and end step are actually just thin wrappers around similar calls to the ADIOS library, which reflects its step-based interface that was designed with scientific applications in mind. Now, the processor is a little bit more complicated. It needs to concurrently handle a high bandwidth data stream and launch a large number of computational kernels. We use the packages MPI for Pi, Q, threading, and ADIOS2 to implement this demanding workload. Especially, we are using the pool executors implemented by MPI for Pi. XANL defines the execution space for the analysis kernels. XFFT defines an execution space for the short-term Fourier transformation, that is, the FFT. The reader object handles ADIOS communication, and as we noted earlier, the task list is an abstraction of the data analysis pipeline. Now, we are using a queue to connect the ADIOS2 communication and the work dispatcher threads. The queue also acts as a buffer. And finally, we are using an array of worker threads to move time chunk data from the queue to the analysis pipeline. Delta combines queue, threading, and pool executors to facilitate non-blocking I/O and compute with high concurrency. In the main loop, the processor receives a time chunk from the stream and puts it into the queue. Once the stream is empty, it exits this loop. Now the worker threads all execute the consume function. There, they read time chunk data from the queue and start the analysis pipeline. And once the queue is empty, the worker tasks return. At the beginning of the data analysis pipeline comes a Fourier transformation of the time chunk data. As noted earlier, we are using the short-time Fourier transformation implemented in Scipy. With the Fourier transformed data at hand, we continue by computing the individual spectral quantities. I'd like to point out here that this implementation is not necessarily the fastest. One could combine the execution of an FFT with the analysis kernel. Now this would require 4 times as many FFTs, but the data would be available directly at the local MPI rank. The point here is that one has to consider both compute time and communication time. Now we've come to the end of the analysis pipeline abstracted by task list. The task class implements the actual launch of the analysis kernel functions through the calc function. Once the kernel returns, the result is stored immediately. This way we can launch tasks in a fire and forget way. There are no dependencies between them. In our code, we keep passing keyword args, which are used in different ways, as parameters for the kernel launch and as metadata for the storage backend. In the submit call, we allow to distribute the calculation of the spectral quantities for all 18,000 channel pair combinations among multiple calls to calc through the getDispatch sequence member. Now that we have looked at the implementation of Delta, I would like to continue and show some benchmark results. Okay, let's keep in mind that Delta is a complex framework consisting of multiple components. That means its overall performance depends on both the performance of the individual components and on their interaction. Starting with the smallest components, let's take a look at how well the analysis kernels perform. These calculate the spectral quantities S, C, P, and R, and we implemented them in Python so they can use multiple CPU cores, circumventing the global interpreter lock. In our experiments, we found that their wall time decreases linearly with the number of threads, up to 16 threads. That is, we have strong scaling. Now, when we run combined MPI OpenMP applications, we need to consider that the total number of CPUs is divided among MPI ranks and the number of threads. Increasing the number of threads makes less MPI ranks available, which in turn leads to less communication among the MPI ranks. From the benchmark results shown here, we conclude that 16 threads are a good choice on the architecture we are running Delta on. Now, as I mentioned in the last slide, The performance of the total workflow depends on the performance of the individual components and their interaction. And a good way to measure performance is to benchmark an example workflow. Now, the example workflow we are considering here consists of calculating the spectral quantities S, C, P, and R for all 18,336 channel pair combinations for 500 time chunks. We benchmark with the workflow setup in 3 scenarios. In scenario 1, only the processor is running on Cori. It reads data from a local file. In scenario 2, data is streamed from the generator running on the NERSC DTN to the processor running on Cori. Scenario 3 refers to the setup where the generator runs at K-star and a middleman on the NERSC DTN forwards data to the processor which runs on Cori. All 3 scenarios were run on a 32-node allocation on Cori with 2048 CPUs partitioned into 128 MPI ranks and 16 OpenMP threads each. The first insight from the benchmark is that the workflow is not constrained by I/O. The plot shows horizontal bars, whose length mark the duration with which a given time chunk is in the queue. The bars start when the time chunk is enqueued, and it ends when the time chunk is dequeued. We see that the arriving time chunks spend longer and longer in the queue, piling up. In other words, the queue acts as a buffer. Also note that the time where the first time chunk is enqueued varies with the scenario. In the file scenario, the processor opens I/O as soon as it is ready. In the 2 and 3 node scenarios, the processor needs to wait for the data stream to arrive. Other than that, there's little difference between the scenarios, and time chunks enter and leave the queue at approximately the same rate. Looking at the performance of the Fourier transformations, we find that it is roughly the same in each scenario. The FFTs are executed immediately after the chunks are dequeued without any delay. On average, the execution time, including MPI communication, is about 0.8 seconds. As a final piece, let's look at the execution timing of the analysis kernels. The plots show wall time of the processor on the x-axis and MPI rank on the y-axis. Horizontal bars in the plots correspond to the execution time of analysis kernels and are color-coded. Blue bars denote cross-phase kernels, yellow bars denote cross-power, red bars denote cross-correlation, and green bars denote coherence kernels. For all scenarios, we can divide the execution in 2 phases. Phase 1 corresponds to a wall time approximately less than 150 seconds, where FFTs are still executed. Here we observe that only 16 MPI ranks execute analysis kernels. Ranks 1 to 4 on the local host are always busy. Other than that, there is little wait time between execution of analysis kernels. Once the FFTs are finished at a wall time approximately larger than 150 seconds, all 120 MPI ranks execute analysis kernels. We now see a different pattern of execution, where there is more wait in between the kernels. We also observe that the execution starts synchronized. This pattern is not visible for ranks 1 to 4, which show very high CPU utilization. As a takeaway from this benchmark, let me highlight that Delta performs the reference workflow in under 6 minutes in all 3 scenarios. That is, with either file-based I/O or when ingesting the dataset as a stream arriving from across the Pacific Ocean. In the current configuration, we could use Delta as a tool for intershot analysis. Note that we observe only minor package loss with the streaming scenarios, 3 and 7% for scenarios 2 and 3 respectively. We pinned this down to issues with the 0MQ streaming implementation and have developed a fix that we hope to use soon. And with this, I would like to conclude my talk and present outlook for future work. Repeating the takeaway message from the benchmark, I hope I convinced you that we can use Delta to reliably perform high-velocity streaming analysis in a time frame usable for intershot analysis. To address some issues we are currently working on implementing, let me say that the ECE workflow only serves as a prototypical workflow. So we are working on implementing other workflows, including machine learning algorithms with Delta, and are making necessary changes to its architecture to facilitate these. We are also aiming at making Delta more adaptable and reduce its streaming data footprint. Possible ways to do this is by filtering in real time which data to send for in-depth analysis to HPC systems, or by using compression. And another issue we need to address before making Delta a workhorse is scheduling. For deployment, we require real-time co-scheduling between plasma discharges at experiments and compute time at HPC sites. Finally, feel free to check out Delta on GitHub. There you will also find the live dashboard that we are currently using for data visualization. And that is it for my presentation. Thank you very much for your